Okay, so it's nice to be here. Thanks for the invitation and the CPO folks for reaching out to us. One of the great pleasures of my life is I'm an amateur and a professional astronomer, so I get to do both things. And so my professional colleagues love it because I know where constellations and how to find the Andromeda Galaxy and stuff is. But as a professional, I get to come and talk to you all about stuff that I get to do every day. So I always appreciate the opportunity. I am a gravitational wave astronomer. Some of you may know we just celebrated the 10-year anniversary of the first discovery of gravitational waves, so we're all still in party mode and enjoying ourselves. I offered to do the gravitational wave talk, but they wanted to hear about dark energy and dark matter, so that's what we're going to talk about today. Okay, so I am at Clarkson University, which is in northern part of New York, right outside the Adirondack Park. We've been living in Chicago for the past 10 years, so I have not been enjoying my evening astronomy life so much in Chicago. But outside the Adirondacks, it's about as dark as it is here at Cherry Springs, and so we've really enjoyed. We observed last night. I brought my 12.5 with me, and so we had a great night observing. It's really a fantastic sight here. It's really been great to be out. So I am going to talk about dark matter and dark energy tonight. You all may have heard something about this. I'm going to tell you a little bit of the history, and then I'll tell you about some of the things that we know. As we go along, if you have questions, please ask them as we go, because if you're confused, almost certainly the person 2 people down from you might be confused as well and isn't as brave about asking questions. I would rather people go along with us. So if the questions get out of hand, I'll kind of tie them off and we'll save them to the end. But if you do have questions, please ask. Okay? If, as always happens, 2 weeks from now, you wake up at 2 in the morning, you'll have some question you wished you had asked me. And most of you, if you haven't discovered it yet, you will discover that your significant other doesn't want to talk about astrophysics at 2 in the morning. And when that happens, my email address is right here, slarson@clarkson.edu. And if you email me when I get in from the telescope, I'll do my best to send you a YouTube video or something to read or try and answer your question if I can. Okay? This is my blog, rightscience.wordpress.com. It is a public-facing blog. I write about lots of stuff there. I write about gravitational waves and black holes and cosmology and dark matter and aliens and SETI. And it's really so my mom knows what I do, so it should be accessible to all of you one way or the other. Okay? And there's my social medias if you're on social media. So, okay. So turn on my clicker here. So to start with, I want to tell you what we're talking about, just to kind of level the playing field for everything. And we're going to talk about 2 things which have very similar names. We'll talk about how astronomers are bad at naming things. But they're kind of about completely different things that we see going on in the universe. Okay? So the first thing is dark matter. Okay? Dark matter, its principal property is that it doesn't emit light of any kind. You cannot see it in a telescope. Whether it's a visible telescope, a radio telescope, an infrared telescope, a gamma ray telescope, it doesn't emit light. We observe it by its gravitational effects on other things in the universe. That's how we know it's there and why we're confident it's there. We'll talk a little bit about that. Okay? I have just told you literally everything we know about dark matter. Okay, and we write entire PhD theses about what I just told you. Okay, literally that's everything we know, and we'll talk about that. Okay, dark energy is also not observable by any telescope. It's not something you can see via any technology that we currently have in our suite of astronomical tools. Okay, we know it's there because we observe its gravitational effect on the expansion of the cosmos. Okay, so the cosmos isn't behaving quite the way we thought it is. It must be this thing called dark energy. Okay? I've literally just told you everything we know about dark energy. Okay? These 2 things have been, and I predict will continue to be, the greatest and most confounding mysteries in astronomy for at least the next century. Okay? And as we'll talk about with dark matter, we've already been going a century, and we still don't know what it is. And so I'm confident, I'll bet you a Dr. Pepper and a bag of jelly donuts that 20 years, when we come back here for the next Star Party and talk about this again, then, we're still not going to know what it is. Okay? No takers? Okay. I have a lot of these bets in my pocket. I'm going to have a lot of Dr. Pepper. Okay, so let's talk about this. So let's start with what is the universe made of and how do we know? Okay, so some of you may know some of this story, but let me tell it so everyone's here so we can talk about dark matter. So the real story about how we know what the universe is made of really begins with light. The thing that all of you and I use as astronomers to probe the universe has been light. And it's through our ability to harness light and dissect light and understand what light's all about that we have learned what the universe is doing. And that's really quite remarkable because no human, now or in the past, has ever been farther from the Earth than the moon. And no one here, no Apollo astronauts, right? Okay, none of us here have been farther than the moon, but we talk about Mars, and we talk about comets, and we talk about the Andromeda Galaxy, and we talk about quasars like we know what they are. How do we know what they are? We have dissected their story by understanding how to harness a little bit of physics, how to harness what light encodes and tells us about the cosmos. So how did we figure that out? Okay, it really started in the 1800s. So this is William Wollaston. So Wollaston was very famous and quite wealthy in Europe. He is famous for discovering palladium in 1802. And the way he discovered palladium is he had invented, and kept very secret and close to his chest, methods for purifying platinum. Okay, and in his purifications of platinum, he discovered that there were things like palladium. Okay, and so this kind of kicked off what turned into a century-long expedition of trying to understand what you and I call the periodic table. Okay, but Wollaston was deeply involved in, it's not alchemy, it's what you and I would call chemistry, but it was really just trying to become rich by doing chemistry on the stuff you can find on the ground. Okay, and in 1807 he was, doing his thing, and he discovered that when he looked at a solar spectrum he had projected, okay, so people had been studying the solar spectrum since the 1600s, he noticed that there were 7 dark lines in the spectrum, as if certain colors of light in the solar spectrum were missing. Okay, and this was completely new. No one had ever seen this before. Okay, so they were given names A, B, C, D, E, F, G, and it's like, what are these? We don't know. Okay. But it's kind of intrigued people, okay? So, as with all things in astronomy, when we discover something new, what's usually limiting us is our technology. So people are like, I want to understand this better, I better build better technology. And so people began to work on what you and I call a spectroscope and improving the technology. So, in 1814, this guy, Joseph Fraunhofer, had invented what you and I would call a proper spectroscope. He basically took that spectral projection and he harnessed it with a telescope or a microscope, something that would magnify and give him a very high resolution view of the projected light that comes out of the prism. Okay? And so he was using his spectroscope, trying to develop it and understand. Yes, back there in the question.
So how did Wollaston find the absorption lines without a spectroscope if the spectroscope came 12 years later?
Yeah, so the question is, how did he discover the absorption lines without a spectroscope, right? And so you can see projections in a spectrum if you are doing it in a dark enough site and if you are projecting it large enough. And the truth is, I don't know what Wollaston's setup looked like, but you can see absorption lines, broad absorption lines, if you have the right conditions. Okay? Great question. Other questions? Okay, so Fraunhofer took it to the next level, though, which is really the follow-on to your question. Fraunhofer did. Okay, and what he discovered, he looked at the sun. Okay, and then he looked at candle flames, and then he went back and he looked at the sun again. And the first thing he discovered is that a candle flame has a bright orange line at exactly one of the dark lines that Wollaston had seen in the solar spectrum. And that's what caused Fraunhofer to then go look at the sun. But his instrument was way better than Wollaston's. And so what he saw is he saw 574 dark lines in the solar spectrum. Okay, and we had no idea what these things were. Okay, this is a picture of Fraunhofer's original sketch of his 574 dark lines. Some of you may remember when you took a physics lab in high school or college, they probably made you do this exercise with a really crummy spectroscope that didn't show you 574 lines. But I have my own version of this in my lab book that I sketched out. But this is Wollaston's. You can see it. It's on display at the Adler Planetarium in Chicago. You can go see it. Okay? Fraunhofer's, yeah, this one. This one right here. This is a picture of the one. Okay, so 574 lines. What are these things, right? We don't know. Okay, but we've improved on the technology. Okay, so let me show you what this looks like today, and then we'll talk about them. So to do this, I want you to think about last night, the Big Dipper was kind of low in the northern sky, so I couldn't see Arcturus. It was behind the trees if it was up at all before dark. Was it up last night? Okay, so imagine Arcturus right when it gets dark. You can see it tonight if you didn't see it last night. And I'm going to show you the sun spectrum, and then I'm going to show you Arcturus's spectrum. And I'm going to show you them back to back. So this is what a modern solar spectrum looks like. This thing is super long, and we've just cut it and lined it all up so you can see it from top to bottom. And there are way more known solar lines now than the original 574 that Fraunhofer found. Okay? Now, I'm going to switch back and forth between the spectrum of the sun and the spectrum of Arcturus. Okay? And what I want you to do is I want you to look at one particular line here, and when I switch back and forth to the other spectrum, just pay attention to what happens to that line. Okay, does it look different? Does it stay the same? Does it appear? Does it disappear? Okay, has everyone got a line they like? Okay, so I'm going to switch. Here's Arcturus. Here's the sun. Here's Arcturus. Here's the sun. Here's Arcturus. Here's the sun. Okay, so if you just experiment with the lines, without even knowing what the lines are, it tells you this has something to do with the properties of the object that we're looking at. Okay, and the people who really figured this out in the end were our friends who are the chemists, but the astronomers were the ones who really pushed us down this road. Okay, and so the long and the short answer is that these lines are the signatures, the fingerprints of the stuff that everything in the cosmos is made of. Okay, and if you and I remember our chemistry class, we were shown and taught this periodic table. My daughter's a chemistry major now in college, right? So she loves this. This is her bread and butter. But this isn't how astronomers think about the universe. Astronomers think about the periodic table this way. Every single element, just like every single person, has a unique fingerprint, a unique set of lines that if you see them in a spectrum, it says that material is in the object you're looking at. Okay? My favorite story about this is the element helium. Do you know where we discovered helium? On the sun. That's why it's called helium. We knew about it in the spectrum of the sun long before we had ever found it on Earth and filled balloons with it. Okay? Okay, so this is how astronomers think about the universe. And every bit of light that you collect from every object that sheds light, you can pump it through a spectrograph and look at the lines, and it tells you what it's made of. Every time you hear a discovery about a new organic molecule or a new gas content of a nebula or how old a star is, we have discovered it by doing this kind of spectral analysis. Okay? Everyone good? Okay, so let's talk then about what the universe is made of. We can discover what everything in the universe is made of. And so in our mind, I'm going to say, let's go pick an object and grab 10,000 atoms out of it and sort the atoms into what they're made of. But when I'm talking about stars and galaxies and stuff, what I'm really saying is, let's look at the spectrum, and we're going to figure out what the relative composition is of these 10,000 atoms. But I'm going to talk about it right now like you and I have little piles. Okay? So let's pick an organism, any organism on Earth. Me, you, your cat, a tree, a frog, or who'd I pick? Kangaroo. Okay? Every organism on Earth has roughly the same balance of elements that we're made of. Okay, this is part of the understanding that I was going to say we astrobiologists, but I guess it's actual biologists on Earth, right? But it's why we as astrobiologists, biologists, think that all life is intertwined and connected, because the molecular chemistry of all life on Earth is essentially the same. Okay, and that the root of that sameness begins with their elemental compositions. So if I just grab a little bit from a kangaroo, okay, roughly speaking, those 10,000 atoms will divide themselves into this proportion of atoms. There's about 6,500 oxygen, 1,800 carbon, 1,000 hydrogens, 300 nitrogen, 150 calciums, phosphorus, potassium, sulfur, chlorine, sodium, magnesium, and other stuff. Okay, where the other stuff is, stuff you ate when you were a kid and probably shouldn't have, right? Okay, so great. We could do that with every organism. They all kind of have roughly the same. But there's other stuff on Earth So if I just go pick up a rock and I do the same thing, quite surprisingly, I get a different set of compositions. There's lots of oxygen. There's lots of silicon. Some of you may have heard the Earth is made of silicates, right? There's lots of silicon, aluminum, iron, calcium, on down the line. Okay? By and large, if the name of something that you see on the periodic table is familiar, there's more of it around us on the planet. That's why you and I know what silicon and aluminum and iron is. Most of us haven't ever seen any technetium or hafnium or any of that other stuff that's on the periodic table. Because when I do this kind of analysis of the stuff around us on the planet, there's just not much of it. It's there, but there's not much of it. The common stuff is the stuff that ordinary folks like me and you are familiar with. Okay? Okay, so we're astronomers. We have spectroscopy at our disposal. So now, what if I do it with the stars? Okay, well, we already gave away part of the story. We said we discovered helium on the sun. But if I could somehow, we've never done this, if I could somehow send an amateur astronomer or an undergraduate to the sun with a bucket to get 10,000 atoms from the surface of the sun, what would I find? And I would find more than 9,000 atoms of that pile are hydrogen. Okay? There's a lot of helium, and then some carbon and neon and nitrogen, and even less of everything else. If I look at those 574 lines on the sun, there's plenty of stuff that's not in this list. And what that means is when I make a whole bunch of piles of 10,000 atoms, every now and then one of them will have magnesium in it, and that one didn't. And another one will have calcium in it, and that one didn't, okay? So this is, 10,000 is far too few of atoms compared to all the atoms in the sun to absolutely guarantee that I get everything we find in the sun, okay? But the lesson here, the important lesson here, is that the sun is mostly hydrogen, okay? Now let's do the game that we astronomers call inference. What's the most common object in the universe? Well, yes, sorry, but I meant stars. And if the sun is like other stars, and the sun is mostly hydrogen, then that means hydrogen is the most common element in the universe. By and large, everything in the universe is hydrogen with some other stuff polluting it. Okay? Okay, and someday we'll do the lifetime of stars, right? The lifetime of stars is how you turn hydrogen into all this other stuff. And some of you know that story. Okay, so, great. We can measure and determine what the universe is made of. Okay, but we can then start taking a census of what's in the universe. And because we're good scientists, even though we know we can tell you what the atoms in the universe are, we want to double check ourselves. We want to know, is what we think actually right? Are we fooling ourselves somehow? Is there some other way to do it? And so what people started trying to do is not just measure what the atoms out there are, they started trying to count the number of atoms in the universe. So let me tell you that story. Okay? Yes, sir?
When you show the dark absorption lines,
Mm-hmm.
absorption line means that that's just what's in the atmosphere of stars.
Yes.
Doesn't tell you what the rest of the star is moving.
Yeah, so the question is, when we talk about absorption lines, we're talking about the outer layers or the atmosphere of the star, which is the light from below comes through the atmosphere and then the dark line removes the light. And so the comment is that doesn't really tell me what's down below. And so that's an absolutely valid comment. There are other ways of measuring farther down in the atmosphere because the emission profile of the light itself has to come from somewhere, and so that's coming from the processes underneath. But we have not been to the core of the sun, and we are inferring what's in the core of the sun. And today, in modern astronomy, the way we do that is through computational simulation, where we can say, let's imagine the center of the sun's made out of calcium, right? And then we simulate what should the surface look like, what should the atmosphere look like, what should the temperature be, what should the light that's emitted look like, and it does not look that way, right? So the core of the sun is hydrogen.
The continuum emission, if you were to magnify that up, would you see closely spaced bright lines, or is it there's no distinction?
Yeah, so the question is if I were to magnify the emission of the sun out, do I see closely spaced bright lines, or is it actually a continuum? And it's actually a continuum. There are reasons for that that's related to something we call black body physics. The sun all stars are a perfect black body, and they emit in the continuum. And so we can talk about that a little bit more if you want to. So, okay, one more question.
You mentioned that the lifespan of a star, we go from hydrogen, helium, etc. So is it the case that we just happen to live in a time in the universe where hydrogen is the most abundant? If we were to evolve some billions of years later, we would have had to infer that it used to be the case that it was mostly hydrogen?
Yeah. So the question is, do we happen to live in a time when hydrogen dominates? Is there some far future in the universe where hydrogen will not? And we think the answer to that is no. And that's because even though the stars are mostly made of hydrogen, there are enormous amounts of unincorporated hydrogen that's never been close enough or enough of it to collapse to form stars. What's interesting is we live in an age in the universe where stars have turned hydrogen into other things. In the very early universe, the stars were pure hydrogen to start with, right? And so one of the kind of current frontiers of stellar astronomy, which is something I work on, is trying to see evidence of those very first stars. James Webb Space Telescope, which we'll talk about later, one of its missions, one of its scientific goals, is to measure the light from those first pure hydrogen stars. Yeah. Okay, I saw one more hand. Yeah.
So when you show your image of all the lines,
The lines, yeah.
what percentage have we figured out and what percentage have we not figured out what they are?
So the question is, for when I show all the lines in the solar spectrum, what percentage of them do we know what they are and what percentage do we not know what they are? So in the sun, I think, I don't know the answer for sure, but I'm just speaking based on other things I know. I think we know almost everything that's in the sun. What happens in other kinds of astronomy, like when we look at planets now especially, and we look at nebulas, is molecules do the same thing atoms do. They make very complex structures, and we don't always know what we call molecular bands are, because we don't know about all the different kinds of molecules in the universe. But we know what all of the elemental, the individual atomic spectra are, and we know what all of those are. So, okay? Okay, that was a good question. Okay, everyone good? Okay, so let's talk, one more.
So when you look at the moon,
Yeah.
and if you do one of those things, is it pretty much the same thing as the sun?
Yeah. Yeah, planets are hard because they have, so the question is, does the spectrum of the moon look different or does it look like the sun? So those are reflected light, and so it's a little more complicated procedure to extract the information about the sun's properties and then the properties of the thing you're reflecting off of. Yeah, but the moon absorbs light and then re-radiates, so we can also get the lunar spectra as well. Okay. Okay, so let's talk about quoting through the universe. So you can't see this right now, I guess maybe right around sunset. Coma's just setting when it's starting to get dark. But earlier in the summer, you could have seen Coma. So let's talk about the Coma cluster of galaxies, okay? So this is a picture of the Coma cluster. It's, it's dense. If you have a big daub, there's lots of great galaxies you can see here. And, it's kind of like wandering through Virgo, right? Those of you who wander through Virgo all the time, there's just galaxy after galaxy. You have to sit there with your randometria and just figure out which galaxy you're looking at, okay? But this kind of high concentration of galaxies in a very small part of the sky is what attracted astronomers' attention when they wanted to start playing this game of counting what the universe is made of, okay? And so the first person to do this was Swiss-American astronomer named Fritz Zwicky. So Zwicky was a professor at Caltech in the 1930s, and he was famous for doing things like 30 years before anyone else did, right? And he'd do things, and he'd write papers, and people would be like, what's Zwicky doing? I don't know, he wrote some weird paper. And 30 years later, we'll go by, and people were like, wow, dude, look what I just discovered. And Zwicky did that 30 years ago. We just didn't know what he was doing. So, okay? So this is the exact same story as Zwicky's doing what Zwicky does. Okay. So Zwicky said, look, if I take a picture of the Coma cluster, that's a whole bunch of galaxies, and galaxies are made of stars. So if I count up how much light I'm getting from a Coma cluster, that should tell me how many stars and therefore how many atoms are in the Coma cluster. And then he said, well, if I measure how the galaxies are moving around the Coma cluster, they're moving around because of the mutual gravitational attraction of all the galaxies, which is all the stars in the Coma cluster. And that is also a way to determine how much stuff there is in the Coma cluster. Okay, so this is a way to check that we're getting the same answer. The light should tell me how much mass there is, and the gravity should tell me how much mass there is. Okay? So Zwicky's like, let's do it. Okay, so this is the result. This is the famous picture. If you go look for pictures of Zwicky, this is the picture that always comes up. Okay, so what he measured is that the gravitational motion in the coma cluster suggests there's 400 times more mass in the coma cluster than the light gives you. Okay? Okay, and if you go through the analysis, it's interesting. I've gone through it. It's this weird, convoluted calculation. But that implies 90% of the matter that you can see in the light is missing. Oh, that's a great question. How do you measure the movement of the galaxy? So we go back to those spectra that we were talking about. So when something is moving, if it's moving towards you, those lines in the spectrum shift towards the blue. And if it's moving away, they shift towards the red. And how much they shift is how fast it's going. Horizontal motion is very hard, especially at those distances. But this motion is easy. Okay. But we use the light. The light's always been our tool. Yeah. Is that based on the wavelength? Yes. So that's called the Doppler shift, for those of you who remember your physics in Intro Astro. And you measure the wavelength, and it shifts a little bit by the amount given by the Doppler shift. Yeah. Okay. So 90% of the matter is missing, okay? So people forgot about this until the 1960s. And then this lady started working on it again. So this is Vera Rubin, okay? In the 1960s and 1970s, she and her colleagues were measuring how individual galaxies were rotating using that Doppler shift we were just talking about, and rediscovered or came back to that idea that Zwicky had discovered in the late 1930s, okay? So Rubin, in 1948, got her bachelor's degree in astronomy from Vassar College. Any Vassar alumni in here? Every now and then there's a few, okay? Okay? And then she wanted to go to graduate school at Princeton, okay? But she didn't. She went to Georgetown. Does anyone know why she went to Georgetown? Yeah, Princeton did not allow women to get degrees until the 1970s, okay? So in 1954, she got her PhD in astronomy from Princeton. In 1965, from Georgetown, not from Princeton. In 1965, she became the first woman who was permitted to use the Hale telescope at Palomar. Right? It seems weird to us now. Like half my colleagues in astronomy are women, and it just seems weird. But this is like within many of our lifetimes, okay? It's strange. Okay, so she was absolutely just kind of one of the most important people in astronomy here through the late 20th century, especially on this problem of dark matter, okay? And I haven't seen one in the wild yet, but she's on one of the quarters that was released this year. Does anyone have one of these? Okay, I'll pay you $1 for your Vera Rubin quarter. Okay, I got to just order one because I have not seen one in the wild yet. Okay, but anyway, she's on the quarter this year because of her contributions to astronomy. She has since passed away. She was an absolutely remarkable woman. She was very, very humble about her contributions to this. She always kind of helped prop up her collaboration and her colleagues, but really she was the one who pushed this all along. So what did she do? Okay, so she did something different. So many of you may know about the Whirlpool Galaxy. Okay, it's under the Big Dipper. I couldn't see it last night. It was behind the trees. But it's famous face-on galaxy. Okay, and it shows you those kind of classic spiral arms like we all imagine the Milky Way will have. It's also cannibalizing NGC 5195 nearby, so that's another reason people look at it. Sometime if we give the galaxy talk, it's very famous as being the first galaxy we detected spiral structure in. Okay, so M51 is just an awesome galaxy to think about and look at. But I show you this because I'm going to show you an animation, and I want you to have this picture in your mind because it will help illustrate what Rubin and her colleagues were measuring. Okay? So what they were doing is they were measuring how galaxies rotate. Okay? And the expectation, if you just sit down and do your physics 1 calculation, is that as you get farther from the center of the galaxy, the stars should slow down in their rotation. Okay? It takes Pluto a lot longer to go around the sun than it takes Mercury. Okay? That's the basic idea. Same thing's true for galaxies. Okay? But what they actually find is that as you go farther out from the center of the galaxy, the stars rotate faster than expected. Okay, so that's what this animation shows. So if you watch this animation, the stars out here are rotating slower than the stars in here. And out here, the stars are rotating far faster out near the edge than they expected to. Okay? So the explanation for this is that there's matter here that you can't see. You can create this effect by taking this galaxy and adding extra matter to it. But we expected this galaxy just based on the light we could see, on where we could see all the stars in the galaxy. Okay, I saw a hand. Yes?
How do you do that with a head-on galaxy if the redshift caused by a lateral?
Yeah, so you can't actually make this observation. You have to look at galaxies that are inclined to your line of sight. Yeah.
But it wasn't M51 that originally.
Nope, I'm showing you M51 so I could show you this video. Okay, in fact, M51 is not perfectly face on. We can measure the rotation in M51, but it's not very much, right? Yeah, okay. Well, I'm going to show you the Andromeda Galaxy. I'll show you Rubin's data for it because it is inclined. Yeah.
Is the one on the left that is deduced from like the ideal pure gravitational impact?
Yeah, so the question is how do we get this motion on the left? So this is, if you sit down, write Newton's universal law of gravitation, use it to derive Kepler's law of orbital motion, this is the galaxy you get. Okay? Assuming this is the galaxy you get, assuming the mass is where the stars are. Okay? This also comes from Newton's universal law of gravitation. It also comes from Kepler's law of orbital motion, but you need mass you can't see to get this one. Okay? So it's all still Newtonian gravity the way we explain it. What we observe is on the right, yeah. Okay, so let me show you. So this, the matter we can't see is what we call dark matter. So this is an example. This is actually Rubin's data. Okay, so this is the Andromeda Galaxy. To the question was asked a moment ago. The Andromeda Galaxy is inclined to our line of sight by about 30 degrees. Okay, so we can see that Doppler shift. And so what you see here is this is the speed of the stars versus radius. Okay. So the higher on the graph, the faster it's moving. The lower on the graph, the slower it's moving. And this radius is relative to the actual radius in the picture. Okay? So initially, the stars are going pretty fast, and they start to go slower as we expect them to. But suddenly, the curve flattens off. Okay? And those of you who have read a lot about this, this is what we call a flat rotation curve. Okay, and this is why we call it flat, is that line is more or less horizontal. The expectation was it would look like a sledding hill, right? It would just keep going down and down and down. Because, as you can see, there are fewer and fewer and fewer stars. But clearly, there's something that's making this happen. And that stuff, as it turns out, is what we call dark matter. There are other ways we can detect this dark matter today. Sometimes we use this. Okay, this is a big daub I saw out in the field last night. No, not really. Okay, this is the James Webb Space Telescope. But if you go look at their first light images, okay, so one of their first light images was this one. This is a Bell 274. I don't remember. Does anyone remember which Bell cluster this was? I don't remember. So, anyways, yeah, some Bell cluster. Okay, but what you'll see here is all of the galaxies. There are lots of them here in the foreground, and then there are all of these distorted streaks, which are galaxies in the background. And the reason those galaxies in the background are distorted is because the gravity of the galaxies in the foreground is affecting the trajectory of the light of the galaxies that are in the background as it comes towards us. Gravity affects how light moves. And so by measuring this distortion, I can tell you how much stuff there should be in all of these galaxies. And guess what? There's more mass than we expect there should be. Okay, there's dark matter there. Okay? So there are lots and lots and lots of different ways that we can prove to ourselves that dark matter is there. We still don't know what any of it is, which is the big problem. So Hobbes walks up to Calvin, who's trying to sell scientific names for $1. And he says, scientific names? And Calvin says, sure, scientists come up with great wild theories, but then they give them dull, unimaginative names. For example, scientists think space is full of mysterious, invisible mass. So what do they call it? Dark matter. Duh. I tell you there's a fortune to be made here. To which Hobbes replies, I like to say quark, 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 quark. And Calvin's like, instead of making an idiot of yourself, why don't you go find me some scientists? Okay? This is the state of affairs, okay? Astronomers, any of you who have taken astronomy, you know this, right? We're very bad at naming things, right? We have been, Zwicky called it missing matter, And Rubin endeavored to never call it dark matter, but we've all just decided we're going to call this stuff dark matter, okay? And that's an okay name. It is dark, it is matter because it influences the world gravitationally, but, you know, that's everything we know about it, so maybe it's a good name, but it's dull and unimaginative, okay? So there are lots of good Calvin and Hobbes strips about scientific names. You can go find them. Go read the one about the Big Bang is called the Giant Horrendous Space Kablooey. And so astronomers actually use that term now, so, yeah, but we haven't come up with a good dark matter one yet. Okay, so this is the problem. The reason this is important is because we're also going to talk about dark energy, and it also is a dull, unimaginative name. And I don't want you to be confused. Okay. Okay, so this is the $25 bazillion question. What is it? Maybe you have a different $25 bazillion question.
Flashlight, would you be able to see it?
That is a great question. If we shine a flashlight on it, would we be able to see it? I think the answer is no.
So how could it be matter?
It's well, right. So let me say why I think the answer is no. I think the answer is no because it doesn't emit light, so we assume it absorbs all the light. The reason we think it's matter is because it has a gravitational field. So for us, matter is the stuff that's in Newton's universal law of gravity, and dark matter certainly seems to fulfill that at the moment. Okay? I see a hand wave around in the very back there.
So what if it's kind of like it has properties of a black hole, but not necessarily the well, you know what I mean? Like not necessarily the intensity of it. Is that ever like,
So I think the question is, could the dark matter be black holes?
like it
Yeah, right. So the answer to that is, we used to think it could be. Then we decided it couldn't be because we couldn't figure out how there are so many black holes. Now we gravitational waves from black holes, and now we're thinking about that idea again. So the answer is probably, and if you want to write a PhD thesis about it, come talk to me.
You showed a photo with gravitational lensing.
Uh-huh.
But we also suspect that perhaps the dark matter is absorbing some or all of that light. Does that mean that what is distorted is dimmer than it would have been if it were gravitationally lensed by normal matter?
Yeah. So the question is basically, how does the gravitational lensing work? Does it absorb some of the light and distort it, and does it change how the distant objects look to us, right? So in the context of the image I showed you, the light that was coming to your eye did not pass directly through the dark matter distribution, or we don't think it did, okay? And so any dark matter that would have been absorbed wasn't on its way to you anyways. The light that came to you, if the dark matter's here, it was going over here, but the gravity of it pulled it and made it go this direction. So there's probably some effect there, but the bulk of the light that I was just showing you was not absorbed or changed in any way.
But in fact, we could infer that whatever was emitting that light is brighter than what we see because some of it...
Yeah. In fact, there's a magnification effect from the lensing, and we can use that to see dimmer objects than normal. Just like your telescope, right? Your telescope is focusing light down. Gravitational lens can also, and we'll talk about that in just a minute. So, okay. Yes, sir. Last one.
Okay. Maybe I'm not explaining this right. Okay, so
Maybe I'm not explaining it right.
Let's say this is a galaxy.
Okay?
Let's say this is another galaxy.
Mm-hmm.
Now let's say galaxies have positive and negative sides to them,
Okay.
like a magnet.
Okay.
So if either positive or negative either could be closing in or repelling. So could dark matter be not really physical matter, but some type of force?
Mm-hmm. Okay. So the question is kind of imagining something dark matter could be besides matter. Okay, and I would say for both dark matter and dark energy, there is a corner of our community that is working to understand whether or not we're not just confused about the law of gravity. Okay, and that is a very real possibility, but it's one that we have not seen any tests to suggest that gravity as we understand it is wrong, but that doesn't mean we're not looking for it, right? So I would call that modifications to general relativity. It's more prominent in the dark energy community than it is on the dark matter community. But there are people who think about it in the context of dark matter, absolutely. Okay? Okay, that's a good question. Okay, so what is all of this stuff? As I already told you the answer, right? We know what it is, right? But let me tell you to answer this woman's question back here, let me tell you about how we're trying to figure out what it is, okay? So we have no idea what it is, but one of the things it could be is something called a macho, okay? And so black holes, if they are what we call machos, okay? Machos is an acronym for Massive Astrophysical Compact Halo Object, okay? And what that means is it's a concentration of dark matter, a dark object, in the halo, the area around the galaxy. Okay, so the halo, the Milky Way is like a disk. The halo is the ball that's the size of the disk that the Milky Way is inside. Okay, so maybe galaxies have this halo of dark matter in the form of machos around them. If that's true, could we look for them? And the answer is we could by using this lensing effect that we've been talking about. Okay, so I showed you a picture of what lensing looks like through a telescope. This is how it works. If you and I had a magnifying glass, if we took your teleview eyepiece out on the field right now, and the sun was over here, what that lens does is it takes rays of the sun and it focuses it down to a point. Okay? So you can burn a hole in, an ant pile or your lens cover or whatever it is you want to do. Okay? If you were to replace the lens with a strongly gravitating object, like a black hole, or a macho, whatever it might be, if it's some concentration of dark matter, it has the same effect as a lens. Light that's minding its own business traveling in a straight line sees the gravitational influence, and that gravity bends the trajectory the light's traveling along. And that means if you're standing right here, you see an amplification, a brightening of that object, because you're now getting twice as much light as you got before. Okay? So, in the late 1990s and early 2000s, we did this. We looked at the Large Magellan Cloud. We monitored 10 million stars every night for 7 years. And the idea is if the galaxy, if the Milky Way is full of machos, every now and then a macho might pass in front of one of the 10 million stars in the Large Magellan Cloud and create one of these lensing events that I just talked to you about. Okay? And you know what? We saw it happen. Okay? So, this is a star that you can't see so much, but it's there. It's kind of faint. Okay? And do you see it turn red? Okay? So, for like a week, it got brighter as purportedly a macho went between us and that star, and then it got dim again. Okay? So, we saw 13 of these events, 20 of these events, something like that. Okay, so we're like, great, we've discovered what the dark matter is, right? Yeah. Sure, we don't know what caused the microlensing, but we didn't see enough of them to account for all of the dark matter. Suck. Okay, so what are we going to do now? So now we got to think of new ideas, okay? So what's the other idea? Our particle physics friends, if you have particle physics friends, string theorist friends, right, this is their favorite thing. They propose maybe the universe is full of weakly interacting massive particles, WIMPs. So these are WIMPs versus machos. You see where this is going, right? Okay, so WIMPs, their idea is, well, look, you and I know about all the particles. We know about protons and neutrons. We know about quarks and neutrinos and stuff, right? Maybe there's some strange particle we don't know about. Why don't we know about it? It's weakly interacting. Okay, neutrinos, we didn't know about neutrinos forever because they are weakly interacting. They go right through you, you don't even know it. Maybe there's some subatomic particle that we don't know about. There are many proposed ones. The most famous one these days is called an axion. Okay, maybe these weakly interacting particles are in a massive cloud around the galaxy. They're not in concentrated objects. They're just a haze, a fog of particles that produce gravity but don't change anything else. Great. How do you look for that? Okay. Well, you have to take that idea that they're weakly interacting. They're not non-interacting. They're just weakly interacting, which means they don't interact very often. Okay. So you build an experiment. This is the current most famous experiment. There are other ways of doing this. I'm involved in some gravitational wave ones. You have a gigantic cylinder full of a non-interacting, non-chemically interacting substance like xenon, which is a noble gas. I have a question. Sorry. Is axion a term in geometry? I have no idea. Mathematicians? Axiom. Oh, axiom is a term from geometry. This is axion, A-X-I-O-N, not A-X-I-O-M. Yeah, so close, yes, apparently. Okay, one more question.
So they weakly interact, but they're massive.
Yep.
And so gravity.
They gravitationally interact by their influence, all of them.
There are a bunch of them.
Yep.
Wouldn't we expect them to clump together and create like dark stars or whatever else that would then interact with normal matter?
Yeah, that's a great question. So the question is, why don't we expect them to clump and make stars? They could, but they are. You should think of them more like a gas and less like rocks, right? So the atmosphere here, there's a bunch of atomic molecules here in the atmosphere, but it's not, at least on Earth scales, there's not enough of it to bind together and form a planet like, say, Jupiter did. But we think down at the core of Jupiter is a solid core, right, that started the accumulation of the gas that became Jupiter. So they have accumulated around the galaxies. There's a big ball of dark matter gas around the galaxies. But clumping them together on smaller scales is hard because they're very energetic, they're moving very fast, and gravity has to overcome that to make them clump. Okay? Okay. So, how do we look for them? Well, we build these gigantic purified vessels full of non-interacting stuff. Okay, so xenon doesn't chemically interact with anything. And the idea is if a dark matter particle comes in, every now and then it might hit a xenon atom, it will make the xenon atom get excited, and that xenon atom will emit light that we can detect inside the dark vessel that we have all the xenon in. Okay, so if a dark matter particle hits and interacts with a xenon atom once every 10 billion years, and I have a billion xenon atoms, I should see one of these events every 10 years. Okay, so we've built these at the laboratory scale. We haven't seen one yet. They've been running about 10 years. So now they're building them on enormous scales, like 3 or 4 stories tall. They're in big mines. We're increasing the number of xenon atoms in the hope that maybe we'll see one of these events. Okay, we still haven't seen it. Okay, which means we still don't know what the dark matter is. Okay? So it's still not WIMPs, but it might be machos because we discovered new black holes with the gravitational waves.
How would you separate a WIMP from a neutrino strike or one of the other?
Yeah, that's a great question. How do we know it's a WIMP and not a neutrino strike, right? So when we do these kinds of experiments, we do something called, we measure what we call our backgrounds, right? So we will set our xenon experiment up, we'll bring it close to a neutrino source where we know the luminosity, and we say, how many events do we get from neutrinos? And then when we're monitoring, it's a giant statistics game. Well, we saw 10 events this year. Yeah, but we know there should have been 12 neutrino events, right? So that's the game we're playing. Yeah. Okay, good question. Other questions? Okay. So, this is dark matter. Don't know what it is. We'll see. Is that all there is? Okay, and for, until the late 1990s, we're like, the universe is full of stuff like me and you and dark matter. And then we made a discovery because we're building bigger telescopes, we're measuring new things, and weird things get discovered. And in the late 1990s, we discovered something weird. Okay? So the story here begins with what are called type 1a supernovas. And those of you who know about this in astronomy, measuring distances is the hardest problem in astronomy. And so for years, the standard has been these type 1a supernovas. There are many different ways of making them, but the classic way is you have a white dwarf star. It gets matter from a companion that causes the white dwarf star to expand up to a very precise mass that we call the Chandrasekhar mass, 1.4 solar masses, at which time it explodes. And so every 1a supernova explodes in this way. It explodes at the same mass, which means the nuclear explosion is exactly the same, which means it gives off exactly the same amount of light, which means this is like a guaranteed 100-watt light bulb. So if I can see these things out in the universe, I know how bright it's supposed to be. So if I measure how bright it looks like in my telescope, I can tell you how far away it is. That's what a standard candle is. Okay? So this is me in my backyard showing you this, this distance experiment. These are 2 flashlights that are the same brightness, right? Same wattage. And if I just take one of them, walk closer to you, it looks brighter than its companion. If I take that same one and I walk farther away, it looks dimmer than its companion. So this is the type 1a supernova gain. They're all supposed to be this brightness. And if they look dimmer, they're farther away. And if they look brighter, they're closer. Okay? So we often draw this with pictures, right? If we have two supernovas at a fixed distance, but one is dimmer, then that automatically means it must be farther away. Okay, so this has been the conventional measurement for distances for ages. Okay, as it turns out, there are other ways of measuring distances in the universe, especially outside the galaxy. Okay, and the classic way comes from cosmology. This was Hubble's discovery just more than 100 years ago, which is if you look at galaxies, okay, if a galaxy is farther away from you, it is receding from you at a much higher speed because of the expansion of the universe. Between me and some nearby galaxy, the universe is only stretching a little bit, so the galaxy is moving away from me because the universe is stretching. But if it's farther away, much more of that universe spandex is between me and the galaxy, so it looks like it's moving away from me at a much higher speed. Okay? So if I just measure the speeds of galaxies, that's another way of measuring distances. And so we try and couple this in astronomy. We do that thing we were telling you that Zwicky thought about, right? Is we always want to measure everything we're measuring in a multitude of ways to make sure we're not fooling ourselves. Okay, so if I measure distances with a supernova standard candle, and I measure distances with this expansion of the universe, I darn well better get the same answer. And you all know we don't, right? Otherwise I wouldn't be telling you this story, okay? Okay, so here's the kind of classic thing. Imagine a type 1a supernova, okay? So depending on its brightness, okay, it will be a certain distance away. And depending on its redshift, or the expansion of the universe, it will also be a certain distance away. And we expect all of those distances to be the same. Okay, so brightness tells us distance and that redshift. But what happens when we measure supernovas, and this is what was happening in the 90s, our telescopes were getting better, we were measuring supernovas farther away. When supernovas are close to us, these numbers agree. The redshifts and the brightnesses give us the same distances. But when we get farther away, what we saw is that the distance we expected from the redshift was closer than the distance we expected from the brightnesses. The supernovas were dimmer than we expected. And the farther away we got, the more those two numbers disagreed with each other. So, what's causing that? Well, we thought for a long time we didn't understand type 1a supernovas. For the last 20 years, we've been studying 1a supernovas like you wouldn't believe. Okay, and there are other ways to make 1a supernovas, but we still think they're standard candles. Okay, and so we've settled on the idea that our understanding of how the universe is expanding is what's different. Okay, and so you hear this phrase all the time, the expansion of the universe is accelerating. Our understanding of the cosmology of why and how the universe is expanding is not as accurate as we would like. And the big conundrum, the difficulty that we have right now, is that the way we've been describing cosmology for 40 years is right, provided we put this extra stuff in the universe that we don't know about. And that extra stuff is what you and I call dark energy. Sorry, it's what the astronomers call dark energy, which is a stupid name for it. Because it doesn't mean anything. We don't even know if it's energy. All we know is it's something that is affecting the expansion of the universe. And maybe the laws of gravity are wrong, so we're working on that, because our understanding of cosmology comes from general relativity. But every other test of general relativity looks normal. So, okay, question. Yes. Yes. So the question: have we confirmed that so we can measure this acceleration, as we call it, in a multitude of different ways. They all give the answer, okay, or the same answer. And so what we're really after right now is better measurements of the acceleration, which means we need to be able to measure more supernovas at these distances, and we need to be able to measure them just a little bit farther than we can now. So some of you may know about the Nancy Grace Roman Space Telescope. So this is one of Roman's primary science goals, is to improve the measurements so that we can address exactly that question.
Could it be that the energy that the star is expanding is directional?
So we have, so the question is, could it be something about the stars themselves and the light they're emitting, and right? So we have repeatedly gone back to the question of the stars, and the stellar evolutionary measurements and theories don't seem to give us any clue that that's the problem. The cosmology is far, the cosmological measurements, the expansion of the universe measurements are far less certain to us right now than the stellar measurements. So, and it could in the end still be the stars or some combination thereof, but right now we're less certain about the cosmology than we are about the stars. So, yeah, that's a great question. Question back there, and then we'll polish off and call it a day. So.
So with dark matter, you've got several different knobs you can turn and try to play with it, but you're always, you're stuck saying, well,
Yep.
dark matter. Rotation curves, polar plus circle is big.
Yep.
Balancing. So that's pretty concrete. Do we have any other lever arm, if you will, or some other knob
Yeah.
to turn besides the expansion of the universe to try to get at dark matter? I mean, some sort of dark energy, in some sense that's definitely what
Yeah.
it is. And if we don't have that, is there something you could do if you had arbitrarily
Yeah.
technology?
Yeah, so the question is, for dark matter, we have kind of multiple things we measure, and we're like, oh, that's evidence of dark matter, this is evidence of dark matter, this is. And so are there similar multiple things we can measure for dark energy? And the answer is yes. This story about the supernovas is how we discovered the dark energy. But today, we have other ways that we know it's there, right? So we do it, in particular, probably the most confident way is measurements of the cosmic microwave background can only be fit precisely if we include the dark energy with it. So microwave cosmology gives us measurements just like these do. And they're in sync with each other, right? They agree. And so we have several handles like that. They're more esoteric than kind of conventional astronomy measurements because we're talking about fitting microwave spectra and, you know, these sorts of things. But we do have multiple handles. Yeah. So, okay? Yeah, you and I can talk if you like to. Yeah. So, okay. So let's call it, and then we'll call it a thing. So this is kind of the current picture of the universe. If I make a gigantic pie chart of what the universe is made of, 5% of it is stuff like me and you and rocks and kangaroos and stars are made of. And this is the stuff we learn about in school, right? And we think, wow, this is what the universe is made of. But it's only 5% of the whole universe. And when I was in graduate school, we knew about the dark matter, okay? And that's 27% of the universe. And so this was the great conundrum when I was in graduate school. We can only account for 30% of what we think should be out there. Okay, at that time we weren't sure why we only thought there should be 30%. There were kind of philosophical reasons for thinking it should be more than this. Okay, which I disliked immensely. I'm like, sure, the universe can be 30%. I have this great book that's all about what if the universe is only 30%, right? It's awesome. I love that book. I still have it, right? But right as I was getting my PhD in 1998, they made this discovery. And so now the pie adds itself up. But fully 68% plus 27%, I can't do that math, 95% of the universe is stuff that we have absolutely no idea what it is. Right. That's awesome. That's why we as astronomers have jobs to do, right? So, okay. So dark energy is, interestingly, becoming more and more dominant as the universe expands and kind of begins to thin itself out. So this is kind of also tied into our, someone asked what's the long-term, behavior of the universe in terms of hydrogen. The long-term evolution of the universe is mostly going to be dark energy, which is this kind of interesting thing. So what does it all mean? This is probably one of my favorite pictures is, it's a great thing to do. Just go home, get a big jelly bean jar, fill it with black jelly beans up to 95%, and then put in the rest. And just sit it there to make you think about the universe a little bit every day when you walk by it on your kitchen counter. Okay? And as near as I can tell, this is the best use for black jelly beans, because I hate black jelly beans. So. Okay, so I always like to give people a few things to read. There's been a lot written about this, but these two books are probably my favorite. This is by Katie Fries. She's at Nordica in Sweden now. It's called The Cosmic Cocktail, 3 Parts Dark Matter. It's really a great book. Katie's a really great author. I think you'll enjoy it. And some of you may know Lisa Randall. She's at MIT. She's written a lot of really great books. She's a particle physicist, but she works on gravitational waves and astronomy. astronomy as well. And so this book called Knocking on Heaven's Door is all about the particle physics side of this, and so you all may enjoy that as well. So, okay, so I'm going to call it a time there, and I'm happy to take more questions, but I'll be around this afternoon. And what, are we good? Sorry. We're time to be done. Yes, okay. So we took questions long. If people want to talk to me afterwards, then we can chat some more. Okay? Thanks for your attention, everyone. Thanks for your questions.